Welcome to a pre-calculus video for skill number 41. I can use a graph of a polynomial function to find a polynomial equation. And a backpacker's tip for you is store your rain gear near the top of your pack. And the very simple trivia question is, why would one want to do that? Alright, so this is an extension of a skill that we already have. We should be able to, if we are given a parabola, generate an equation of that parabola just by looking at the roots. Like if you had a root of 1 and a root of 4, then your equation is some number x minus 1 times x minus 4. The extension here is if we turn the quadratic into any polynomial, and maybe our polynomial becomes a degree 3 polynomial that has another root out here at, we'll say this is at 8. So then our function now becomes a times x minus 1 times x minus 4 times x minus 8. So it's really just the same thing we were doing earlier. We're going to find our a value the same way by, it's going to be based off what the intercept is, and we'd have to substitute 0 in. So let's take a look at some examples. Okay, we're going to start with problem number 32, and it's basically writing the equation. And it says that we have degree 3, which means we're going to have essentially 3 parenthesis sets, and our zeros will tell us what goes in those parentheses. So we have a 0 at negative 5, so we have x minus negative 5. We have a 0 at negative 2, so we have x minus negative 2. And we have a 0 at x equals 1, so we do x minus 1. And we still have this a value that's kind of our stretch at the very front of it. So if we were to simplify this equation, we're going to have y equals a times x minus 5, x plus 5, x plus 2, and x minus 1. Because we have a vertical intercept at 0, 6, we can substitute 0 in for our x's and 6 in for our y's, and that will allow us to solve for a. So if we do that, we have 6 is equal to a times 0 plus 5 times 0 plus 2 times 0 minus 1. So we get 6 equals negative 10a. 6 equals negative 10a. Solving for a, we get negative 6/10. So our equation is negative 6/10, or negative 3/5, x plus 5, x plus 2, and x minus 1. There we go. Sometimes you get a case where you have what's called a multiplicity, which means the function has 2 roots at the exact same spot. So here our degree 4 says we have a root of multiplicity 2 at x equals 4, which means, well, first of all, it's 4 degrees, so we're going to write 4 parenthesis sets, and our a in the front, and a root of multiplicity 2 at x equals 4 means we're going to have 4 written down twice. X minus 4, x minus 4, and then a multiplicity of 1 at x equals 1. So we'll have x minus 1. And just off camera here, a root of multiplicity 1 at x equals negative 2. So we'll also have x minus negative 2, or x plus 2. And this is all equal to y. Because we have a vertical intercept at 0, negative 3, we can plug those values in, and we get negative 3 equals a times 0 minus 4, 0 minus 4, 0 minus 1, and 0 plus 2. That's negative 32. So we get 3 equals 4 times 4 is 16 times 2 is 32. So negative 32a, or basically 3/32 is our a value. So to write our final equation, y equals 3/32 times x minus 4. And since we had it twice, let's just write x minus 4 squared, and then x minus 1, x plus 2. So this square shows that we had the multiplicity of 2 there. There's our final answer in factored form. Looking at problem 36, they use a term of 000. That would be the same way of saying a multiplicity of 3. So we're told that it's a degree 5, so we're going to say y equals a, and then we've got x minus negative 2, x minus 3, and then x minus 1, which happens 3 times, so I'm just going to write it 3 right there. So what we've got is 1, 2, 3, 4, 5. So 5 factors, which line up with our degree of 5. And this time, instead of giving us the intercept, they just give us some random point of 2, 4, but we can still treat it the same way by plugging the values in. So 4 is equal to a times 2 plus 2 times 2 minus 3 times 2 minus 1 to the 3rd power. So we get 4 is equal to negative 4a, and from there we're able to conclude that a is equal to negative 1. So our final equation should be negative 1 times x plus 2 times x minus 3 times x minus 1 to the 3rd. Alright, in this case we are doing the backwards version of this, or rather we're looking at the graph rather than having the text tell us the information. So it's a subtle extension. They ask us to identify the degree, then the roots, and use this to write a formula for each polynomial. So in this case I see a function which has 1 turning point, 2 turning points. So there's 3. It's a degree 3 equation at the least. And it looks like what we have are 3 roots, so that kind of confirms or helps support that. So I'm going to go ahead and write in here the degree is 3, and the roots occur at negative 3, negative 1, 0, and at positive 3, 0. And they want us to use that to write a formula. So we use the same process. Y equals a times x minus negative 3, x minus negative 1, and x minus positive 3. And from here we need to figure out what our a value is, and we would do that by looking at our intercept. So we have an intercept at 2, so we can substitute that value in. 2 is equal to a times 0 plus 3, 0 plus 1, and 0 minus 3. Which tells us, if we solve that out, negative 2/9 is equal to a. So our final equation that we'd have is y is negative 2/9 times x plus 3 times x plus 1 times x minus 3. And this kind of confirms our understanding a third degree polynomial has n behavior, which looks like this graph. It kind of goes in a downward direction overall when we have a negative leading coefficient. So that's good. Our leading coefficient's negative. Let's take a look at problem number 40. So problem 40, what we see is another case where we probably have a third degree polynomial, but as you can see, the root here, it touches and then drops back down. So that's called where you have a multiplicity. So write this down. We've got a degree of 3, and then we have roots at negative 2, comma 0, and that's a multiplicity of 2. So this multiplicity means it happens twice. And then we also have a root at 3, comma 0. So when we go to write our equation, we'd say y is equal to a times x minus negative 2. And we square that because it's happening 2 times. And then x minus 3. And again, we're going to go to the graph to find our y-intercept to help us determine what the value of a is. And our y-intercept is negative 3. So we have negative 3 is equal to a times 0 plus 2 squared times 0 minus 3. So that's a should be equal to 1/4. So now we can write our final equation. Y is equal to 1/4 x plus 2 squared times x minus 3. Alright, so I think the rest of these I'm going to leave to you to work through. I'm just going to give a couple pointers. You can see because there's 3 turning points, what we have is a degree of 4 here. Because it opens downward, chances are our a value will be negative. Taking a look at number 4, 44, we also have 3 turning points. So it's probably a degree 4. There's a multiplicity at negative 3. And again, it generally opens downward, so it's probably a negative a value. And 46 looks like we have multiplicity of 2 twice. So we're going to get a factor squared twice. In fact, let's do this. This one we have a degree of 4, and we have the equation y is equal to a times x minus negative 2 squared times x minus 1 squared. That's because our roots happen twice at each of those. So we have roots at negative 2, comma 0, multiplicity of 2, and 1, comma 0 with a multiplicity of 2. Okay, and now we need to solve for a, so we're going to use our intercept of 4 to do that. So if we plug in 4 is equal to a times 0 plus 2 squared times 0 minus 1 squared, we get a is actually equal to 1 in this case. So a equals 1, so our final equation is y equals 1 times x plus 2 squared times x minus 1 squared. And no, you don't need to write this one, but by putting it there, it does show that you've given thought to the value of a. Okay, looking at problem 48, what we can see is we have one turning point, a second turning point. You can kind of think this as a third turning point and a fourth turning point. So we have a degree of 5. And when you see these back-to-back turning points like this, chances are that that's going to be a case where you have a multiplicity. We've seen the multiplicity where the graph comes down and just touches at the point. Well, this is touching basically 3 times. So you can consider that a multiplicity of 3. So we have a root of multiplicity 3 at 4, 0. And then we also have other roots at -2, 0 and -1, 0. So our equation before we solve for a is a times x minus 4 to the third x plus 2, x plus 1. And then we'd want to use our intercept to solve for a. So 4 is equal to a times -4 to the third times 2 times 1. And we'd solve for a. This gave me an a of 1/32. Sorry, -1/32. So our final equation is -132 times x minus 4 to the third times x plus 2 times x plus 1. Alright, I think there's nothing too unique here. Problem number 50 seems to be fairly similar to what we've seen. 49. We've got, let's see, one root, second root, a third root, and then 4 and 5 happen right there with a multiplicity of 2. So I think that's it for the problem set. Alright, so you can see this was a slight extension of being able to graph or use the graph of a quadratic to find the quadratic equation. Now we're using the graph of a polynomial, so a quadratic or even a cubic or fourth degree, etc. polynomial function to find the equation. The answer to the trivia question is the benefit of having the rain gear near the top of the pack is that when rain comes in, you can very quickly access it and get dressed in your rain gear. Thanks for watching.